Good afternoon, and welcome to the second ICCSW15 keynote talk. I'm very happy that today we've got Erik Mueller here. He's got a very strong interest in AI and reasoning. He's written various books on daydreaming and commonsense reasoning, and he's recently been working in IBM Watson, and in particular on the system that competed in the Jeopardy show. So please welcome Erik Mueller.
Hi, everyone. So in August 1955, John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon proposed. They wrote a short proposal to spend a few months the following summer to work on the project of developing an intelligent machine. And they actually held that conference the following summer. And this is actually when they coined the term artificial intelligence. I think it was actually coined by John McCarthy. So here we are now, 60 years later. It's September 25th, 2015. There has been significant progress in a number of areas, and among them, question answering. So, for example, the Watson program, which is a question answering program that was developed at IBM that I worked on, it went on the Jeopardy game show, and it won against human champions at the game of Jeopardy. And it's great at answering fact-based questions like these questions. And they're phrased this way because this is the way they're phrased in Jeopardy. They're actually phrased as answers, but they're actually questions. So like the Prime Minister of England lives here, and the answer is 10 Downing Street. Or on June 28, 1919, this was signed in the Hall of Mirrors, the Treaty of Versailles. But we don't have true AI yet. So a couple weeks ago, I was reading in The Economist, there was an article about all these programs that everyone has now, like Siri, and Amazon came out with this little device that you can put on your table called Echo. And they wrote, Echo, Amazon's product, can recite the definition of personal assistant without hesitation, but it had no idea how to respond when your correspondent asked whether Echo was her personal assistant. True AI would be able to answer harder questions like these, to go beyond simple fact-based retrieval. As good as it was to develop the Watson Jeopardy system, that's really just the beginning. So in today's talk, I'm going to talk about, I'm going to first review the Watson for Jeopardy system because it's interesting. And then I'm going to talk about two attempts that I worked on after the Jeopardy competition to develop systems that go beyond fact-based question answering, basically related to healthcare, Watson for healthcare, and then another system called WatsonPaths. And then I'll talk about what I think comes after that. I think we need to focus on several things, which are arguments in predicate logic, being able to reason about events in time, and using declarative methods. Then I'll also talk about a new proposal to use thought-provoking children's questions as a way of driving AI research. So first, the Watson Jeopardy system. So this was a system in 2011. It won a 2-game Jeopardy match against 2 Jeopardy grand champions. And you can see my ticket there. It was B8. That's where I sat during the competition. And the way Watson works, it's useful to go over Watson because it's kind of an interesting algorithm. It starts by taking a question as input, like what disease causes right upper quadrant pain. Then what it does is it analyzes the question. So it does syntactic parsing of the question, semantic parsing. It identifies entities in the question, like medical entities in this case. It also identifies what's called the lexical answer type, which is the type that you want the answer to be. So because it's asking what disease, so the lexical answer type is disease. It also identifies a thing called the focus, which is the part of the question that the answer can be substituted into. So what disease causes right upper quadrant pain? Whatever the answer is should be pluggable into that, and blah, clauses, right, upper quadrant, pain. So once it's analyzed the question, it forms a search query, and it basically uses a search engine to retrieve documents related to the query. And in the case of Watson, we weren't allowed to have the internet, access to the internet during the competition, so we had to have our own corpus already built into the system. So but it does a search over that corpus, and it retrieves back documents as well as short passages related to that query. So it retrieves those. It also, another step in the pipeline is retrieving answers from structured sources. Of course, we may have databases of things that give answers to questions, so we can also use those as a source of answers. So we then generate candidate answers both from structured sources and also from these passages and documents that we got back. Basically, we may pick out entities that are close in position to the query terms, or other heuristics are used to pick out candidate answers. We don't know whether these answers are the right ones yet, but we also do have the scores that the search engines provided about how relevant these passages were to the query. So we have a bunch of candidate answers with some initial scores attached to them, but not the final scores yet. So now this is actually the second pass of Watson. It now goes and tries to retrieve support or non-support for each possible answer that it's generated. So it generates now a new query that includes the candidate answer. So now let's say cholecystitis is one of the candidate answers. We want to figure out whether that's the right answer or not. So we generate a search query for that, and then we get new passages back. And then we want to score the passages to see whether they indicate that the passage supports the answer. So if it says cholecystitis does not cause upper quadrant pain, that would be an example of it not supporting the passage. But if it does say it, it does support it, and we would give that passage a high score. So we have scores now from the initial search that we did on the previous slide, and we also have scores from all these. There are actually a bunch of scoring methods, and they all generate features that indicate how well this answer is supported as being an answer to the question. There's also now another step, which is to merge equivalent answers using various things like synonym detection and things like that, because we may, by this point, you've actually got a ton of duplicate answers, so we merge them all. The ones that are the same, we merge them into single answers. And then for each answer, we calculate a final score using a binary logistic regression model that's previously been estimated from training data. So we've got all these features, and then we have weights attached to the features that we've learned, and those are then plugged into this formula, and then we get a final score for each candidate answer, which indicates whether that, how good of an answer that one is. So that's the basic algorithm. This slide shows how we drove up the performance of the system over a period of years, starting with the initial baseline system. IBM had been developing question answering systems for at least 10 years, if not longer, before the Jeopardy competition. So there were at the TREC conferences, they had a lot of competition for question answering systems. So the technology was being developed, but we wanted to get it to the point where it could be good enough to compete against actual human Jeopardy players, champion Jeopardy players, and hopefully win. So these dots, whatever color that is, sort of bluish dots, are records of actual Jeopardy games and how well particular players did in those games. And then the red dots are how well Jeopardy champions did at games. And it's basically showing the percentage of time that people answered a question versus what their accuracy was when they did answer. And in Jeopardy, you have to buzz. It's 3 contestants, and the question is read off by the host, and they have to buzz in if they think that they know the answer, and then they get to be right or wrong. So they don't always have to answer. If they haven't buzzed in, they don't answer. So by the end of it, as we were getting close to the competition, we were getting fairly close to the performance of grand champions. And I guess someone gave it the green light. Let's go ahead and do the game and see what happens. So, and we won. So now after the Jeopardy match, we started to develop applications of Watson. And the first project was a project I worked on to adapt Watson to the healthcare domain. And we built a system called Watson for Healthcare. So we wanted to see how hard would it be to adapt Watson to a new set of questions. It will work on any questions, but it may not perform as well as you'd like. So to adapt Watson to a new domain, there are basically two steps. First, you have to acquire any new medical content, any content related to the domain, in this case medical content, and then you have to add new components that may be specific to that domain to improve the performance. So here's what we did to adapt Watson to the medical domain. We first added a bunch of medical content. We licensed, it took a while, but we licensed content from various providers of medical textbooks and dictionaries, encyclopedias, journal articles, and so forth. And we did this thing called content ingestion, which is to bring the content into the Watson system. And one of the main ways we represent content in Watson is using these things called title-oriented documents, TODs, which they're similar to Wikipedia articles. They're things that have a title and the content sometimes broken out into fields. Like a document about atrial fibrillation may have a section called symptoms, which has information about the symptoms, or a section of a document having information about symptoms of that condition. So we ingest articles, and some documents, the corpus isn't necessarily broken down into documents like that, but we have heuristics to create them. Then the next step is to automatically annotate those documents with using our parser, basically using the same NLP stack that we use when we're parsing questions. We run that also on the corpus. So then we store and index those so that the search engine can use them, and we also annotate full text of passages that we've created from the corpus. So then, now here's an example of some new components that we added to adapt Watson to the medical domain. We added question analysis components to use existing resources. There's this huge ontology of medical terminology developed by the United States National Library of Medicine called UMLS, which is actually just a merge of a ton of medical ontologies. We incorporated that into the question analysis to recognize those concepts. We also used that to expand queries, to use medical synonyms to be able to recognize, to retrieve documents that have synonyms of the things that are in the question. And also for answer retrieval, I developed a structured knowledge base called SKB, which was done by mining our medical corpus for relations between medical concepts, especially relationships between medical findings like symptoms and lab test results and things like that, and diseases. And we also added stuff to the answer scorers to be able to recognize synonyms, and also recognizing whether something is an instance of the right type, which is what's asked for in the question. And also when we're merging answers, that provided an additional source of synonyms. So what we decided to use as a way of evaluating this program, Watson for Healthcare, was to use this thing called Doctor's Dilemma, which is a Jeopardy-like competition for medical students. We were able to get the data for a bunch of those contests and use them for our evaluation. It's a lot harder than Jeopardy. For instance, we found one of the first things we found when we were doing this is that there's a lot more variability in terminology in the medical domain than in the Jeopardy domain. Just a thing like lung cancer has many ways of expressing it based on UMLS, and there are probably other ways that aren't even on this list. And it's harder also because we're doing a kind of diagnosis sometimes, because we're given a partial list of signs and symptoms of a disease, and then we have to come up with the diagnosis as the answer. So we acquired 5,000 doctor's dilemma questions from the American College for Physicians. This is what they look like. They're similar to Jeopardy questions, like diagnosis suggested by hypotension, fever, rose spots, and bradycardia. The answer is typhoid fever, stuff like that. So we evaluated it on 188. After we did all this work, we evaluated it on 188 unseen doctor's dilemma questions. And this is showing the results of different stages of the adaptation. So that the top row is showing running the original Watson Jeopardy system on these questions. It got 19.7% accuracy, so 19.7% of those 188 ones right. Then just changing the content in Watson, but not anything else, just adding the medical encyclopedias and stuff, that brought the accuracy up to 27.1%. Then by retraining Watson on doctor's dilemma questions to adjust the weights, that had a big increase. That resulted in 43.6% accuracy. And then finally, all the work we did on adapting the components got us up to 50.5%. This is actually pretty good. The questions are hard because they're open-ended questions, and there are a lot of, its medical domain is quite hard. So that was getting us a little bit toward moving beyond the fact-based question answering. Now, we took an even bigger leap forward with developing the WatsonPaths system, which was the goal was to be able to take medical test preparation questions of the sort that are used to test medical students as part of their process of becoming a physician in the United States, and be able to answer those questions. They're much longer. They're a lot harder than any previous questions we had taken. So the original this new WatsonPaths system is designed to handle more complex questions than Watson. Watson is basically a thing that can perform single-step inferences. There are a few things where it tries to do more than that, but in most cases it performs single-step inferences. WatsonPaths actually performs multi-step inferences by repeatedly invoking Watson as part of that process. Here's an example of one of these medical test preparation questions. So you're given this long scenario about the patient. A 63-year-old patient is sent to the neurologist with a clinical picture of resting tremor, et cetera, et cetera. And then you're given what we call the punchline, which is the actual question that you want to answer for this question. And you're also given multiple choice answers, which is nice because you can then only consider that. It's really amazing how many alternative diagnoses there are in the medical domain if you open it up beyond that. So you're given the question and the multiple choice answers, and here's what WatsonPaths will do with a question like that. This is how it works. It starts with the question, it takes it as input, it then does a new kind of analysis of the question, sort of similar to the kind I described earlier for regular Watson. But it actually starts to build this thing called the assertion graph, which is a node-link graph that have assertions on the nodes and relations between those assertions on the links. And so what we do is we analyze the question and we get relevant medical concepts out of the question, and we create them as nodes in the graph. And we also add the multiple choice questions the multiple choice answers as nodes into the graph. Okay, so now here's where the algorithm gets started. It starts going. So what we do is we ask Watson, the Watson 1.0 original Watson system, questions, sub-questions, and we use the answers to generate new nodes and edges in the graph. So we ask questions about the concepts that are already in the graph, and we also ask questions about the multiple choice answers, and I'll give you an example of that because that's a little bit hard to understand just abstractly. And then we run other edge generators. If we have structured information, we can also use that to generate links in the graph. And then we estimate the confidence in the nodes using Bayesian inference. And a step that we don't use in WatsonPaths if we're given the multiple choice answers is to now generate also some more hypotheses like diagnoses if that's what we're doing. But we don't have to do that in this case because we already are given the hypotheses as the multiple choice answers. And then we've got a loop, and we go back to step 3, and we keep doing this. So we're generating edges, we're generating nodes, and until some stopping condition is met, and then we stop, and we return the multiple choice answers along with the confidences that are attached to those answers. Now, here's an example of that, so you can see what I was talking about. So the unexpressive face was a sign and symptom in the question. That's added as a node. And then the substantia nigra was one of the multiple choice answers. So what the algorithm will end up doing is asking a question, in what disease is the substantia nigra most likely affected? So then Watson will come back with a bunch of answers with associated confidences. And one of those answers is Parkinson's disease. And then other answers. And so we connect that node with a link, location of, which we've got this ontology of relations that are associated with particular types of questions. So we know what type of link to generate there. And also, we ask questions starting from the signs and symptoms in the question. So we ask what disease causes unexpressive face, and that will give us back a bunch of answers, and one of those answers is Parkinson's disease. So we actually, instead of adding it as a node twice into the graph, we're smart enough to realize that it's the same thing, and we only create one node in the graph. So now we've got a kind of graph, and where we've got this node in the middle that was inferred. That's actually the correct answer. Surprise, surprise. That's basically how it works. So what we did was we did a comparison of the original the Watson for Healthcare system with this new WatsonPaths system. So we ran it on 500 unseen medical test preparation questions. And we did it for all of the questions, but we also did it for just the diagnosis subset because those are a lot easier. And it's also of interest to doctors. So we also retrained Watson for Healthcare on another set of medical test preparation questions. So it was retrained, but it was nothing else was changed besides that. And we found that the new system did perform significantly better than just the Watson for Healthcare system. Okay, so now I'm going to talk about how I think we can take question answering further. To deal with the richness of human knowledge, we need to move to something closer to predicate logic. So in practice, Watson uses mostly propositions and a single connective of implication. So if you think about those nodes, we've basically got a thing like circular rash, and it's connected by a link to Lyme disease, and that's connected maybe by a link to a treatment like doxycycline. But for the medical domain, there are a lot of cases where connectives would be extremely useful. For example, there are all sorts of pieces of medical knowledge that are conveniently represented using connectives. If you don't have an enlarged thyroid, then that actually rules out hyperthyroidism. If you have jaundice and a palpable gallbladder, that actually rules out hepatocellular jaundice. So as you can see, negation is a very important thing in medical diagnosis. And then there's a lot of different ways of defining diseases. Some diseases have diagnostic criteria which actually specify what the definition of the disease is in terms of other things. So if those things are true, then you can infer that the disease is present. An example of that is this definitional thing. If you've got aortic dissection and aneurysmal aorta, that is by definition a dissecting aortic aneurysm. In cancer, there are definitions that the pathologists use for particular types of cells and patterns that are what the definition of particular types of cancers are. So if you have irregular infiltration of stroma and variable ductal formation by infiltrating cells, that's infiltrating ductal carcinoma. There's also another thing in the medical domain which is called a syndrome, which is, they're sort of diseases that aren't really well understood as to what causes them. So they're actually defined in terms of a suite of symptoms. So cataplexy is defined as a sudden and transient episode of muscle weakness and full conscious awareness. And this last one is a definite sort of definitional thing. They experts in heart, the area of cardiology, have defined ventricular tachycardia as a pulse rate of more than 100 beats per minute and at least 3 irregular heartbeats in a row. This phenomenon is particularly important in the area of psychiatric diagnosis. In the United States, we have this thing called DSM-5, which is a definition of all the psychiatric disorders. I'm not sure if they use that here. I think it actually wound its way into the ICD-10 standard, which is a medical coding standard, which uses a lot of the same ones. But I think according to this DSM-5, everyone in America has some kind of psychiatric disorder. No, just kidding. But they define it, again, these are definitional things that you can do. If someone has if they have palpitations, dyspnea, chest discomfort, nausea, numbness, and they're worried about going insane, you can conclude that they have a panic attack, that they're having a panic attack. So I think that, so Watson attempts to retrieve knowledge on demand by querying corpora, but I think that there's, in certain domains like the medical domain, there's a finite amount of knowledge, and it's to some degree codified by the medical field and specialties, so that it actually, I think it'd be useful, to extract, correct, and refine knowledge in advance rather than trying to build it on the fly. So I think it's kind of too complex to be left to chance. Another aspect of this, so this is all under the rubric of sort of moving, getting more of logic back into sort of systems that use unstructured information, because it can add value. So another example of that is the fact that we need arguments. A lot of the stuff I see, again, is so propositional, but you need arguments sometimes. If it says something like the patient's mother has high blood pressure and diabetes, you have to know that's not talking about the patient, it's talking about the patient's mother. Now, the second thing that I think is important is to deal with the real world, we need to be able to reason about a lot of things that are common in the real world, like events and time. So a very simple example of that is just something like, her medical history is notable for jaundice 10 years ago that resolved. And we have to know that the patient does not now necessarily have, does not have jaundice because it's resolved. And here's an example where you have to know about time. There's this thing, tachycardia, which is a fast heart rate, and bradycardia, which is a slow heart rate. They're inconsistent with each other. But there's actually, sometimes you get these questions that are talking about something like, there's this asthmatic patient who has bradycardia, and they have a low arterial blood oxygen tension level, and what's with them? And there are kind of two possible things, asthma attack and impending respiratory failure. But the trouble is, asthma attack initiates tachycardia. It makes you have a fast heart rate, but low blood oxygen saturation level makes you have bradycardia. So they're actually both possible diagnoses, but they seem to be inconsistent if you don't take account of time. So you have to take account of time. It could be the tachycardia happened from the asthma attack, and then that was followed by bradycardia that resulted after that blood oxygen saturation level caused hypoxia. And obviously, in domain that I like a lot, which is the story understanding domain, you need to take account of events in time. There's a RoboCup, this RoboCup competition. They have narratives that are the descriptions of these kind of like commentators of the RoboCup competitions. And you can try to reconstruct, they also have the actual RoboCup formalized representation of what happens in the RoboCup games. So you can try to reconstruct those formalizations given the narratives, and that's a nice, clean story understanding task to try to work on. You have to use events and time to do that. Also, I have this paper where I propose this story understanding task where you answer a lot of questions related to the goals and needs and wants and things about the characters in the story as it's unfolding, and obviously events and time are important for that. And then now the third thing that I think is important to put back into some of these systems that use unstructured knowledge and machine learning is declarative methods. I think declarative methods are very useful as a way of finding models and keeping them kind of separate from one another, so you don't have just spaghetti of a lot of concepts and you can't really make sense out of it. So declarative methods are kind of a cool thing. Instead of writing a program to solve to solve a problem, you describe the problem, and then you let the computer figure out how to solve it. And it's great for finding models of the narrative, which is, again, my pet problem. There's also a lot of psychological research, starting with Craik's The Nature of Explanation and mental models of Johnson Laird and so forth, that sort of talk about how story understanding is creating a model in your mind of what's happening in the story. One example of a declarative method is answer set programming, which is you take as input a declarative representation of a problem, and you then output, the solver outputs 0 or more solutions to that problem, which are called stable models. And there are a bunch of answer set solvers that you can download and run. The most recent one is Klingo. It works quite well. And here's an example of what this can do for you, keeping things separately. If we have a simple formalization of like, if someone goes, they're either running or driving. This is a disjunctive rule at the top. And also, if they run, they're tired. And so you can say at the beginning, Nathan wasn't tired and he went to the bookstore. But you don't say how he got to the bookstore. If you run this through an answer set solver, it'll give you the two solutions that are, entailed by that formalization. One in which Nathan drives to the bookstore and is not tired, and another in which he runs to the bookstore and is tired. Just a simple example of that. Here's an example in the medical domain of using declarative methods and keeping multiple models separate. If you're given an input, someone's in the question that says high ornithine, but actually it's very critical whether it's high urine ornithine, which indicates one thing, or whether it's high plasma blood ornithine, which indicates another thing. So you can do that. You can formalize this again using disjunctive rules, and you can run it and put it through the model finder, and it will give you back the two answers. It'll simultaneously disambiguate the input and provide you with the corresponding answers that would result from that disambiguation. Here's also just a simple example of using answer set programming to answer the question, how many ways can you make, I forgot to change this to 20 pence, using pennies, nickels, and dimes, and you just pretty much can type the formula in and it'll give you back answers. Or here's an example of a fourth grade physics science test problem, which is basically a constraint problem. You're given a bunch of things. The number is more than 5, the number is less than 15. When the number is divided by 2, the answer is an odd number. When the number is divided by 3, the answer is an even number. You can just type that into answer set programming and get the answer. So the event calculus, which was invented here at Imperial College in the 80s, is an example of a formalism that embodies the three things that I'm saying we need to pay more attention to: predicate logic, reasoning about time, and declarative methods. My book on Commonsense Reasoning discusses the event calculus in detail. The first edition came out in 2006, and I just came out with a second edition this year, which has a completely updated text. It has 3 new chapters on various developments that have become more prominent. They did exist in the first edition, but they've become, a lot of work has been done on them since then. And so there's a separate chapter on answer set programming, on unstructured information, and on acquiring common sense knowledge. And there's several new appendices and sections. So I'm not going to really talk about in detail the event calculus, but just briefly, some of the notions are events, fluents, and time points. An event, a predicate happens that expresses that a point event happens at a time point, just like an instantaneous event happens at a time point. Another predicate is holds at, which says that a fluent holds at a time point. And so using those predicates, we could represent something like a narrative like Mark turns on the light at time point 1, the light is on at time point 2, he turns off the light at time point 4, and and the light is not on at time point 5. I'm not showing how the machinery works. The machinery is, you can use various axiom sets for describing how to actually make those inferences. You can look that up if you're interested. To actually run the event calculus, you can go to this web page and download some answer set programming axiom sets for the event calculus, and then you can run them with the Klingo answer set solver. Okay, so now I'm going to talk about kind of over the last couple of months, I've been working with Henry Minsky on a new AI challenge problem. There is a magazine in the US. Has anybody heard of Highlights magazine? No. It's for children. There's a feature called Brain Play, which is questions and activities for stimulating children from 5 to 12 to think and reason by working over in their heads what is already there, arriving at new ideas not learned from books. So this not learned from books is a lot like common sense knowledge. It's a great thing for exposing common sense knowledge. This is what it looks like. And some of the examples are simple, but some of them can get pretty hard, especially hard for computers. Can you list some sounds that can be mistaken for each other? What do you do to cool off when you feel hot? Here's some more. These are some of the hard ones that really show how far we have to go in AI. Like, which takes longer to peel, an orange or a banana? Why don't raindrops always fall straight down? Do you think a car feels thirsty when it's low on gasoline? I like this one. Why doesn't every key open every lock? Which is older, a tree or a leaf on the tree? Why aren't pants pockets as big as backpacks? If you tried very hard, would you be able to see through a brick wall? I think these questions are wide open. I mean, not to humans, but to AI systems. So here's a basic task definition. Given a thought-provoking children's question, produce one or more answers. But I also think an interesting thing about these questions is they actually create learning in the child, and they allow the child to come to new conclusions and learn new generalizations about the world. Like, even in this simple case, name some animals that hatch from eggs: birds, chickens, ducks, snakes. It seems like animals with feathers hatch from eggs. I don't know if this is true, but it seems like from that. And another aspect of it is the mental, sort of the thought experiment aspect of it. You can learn from doing real experiments, but you can also learn from doing imagined experiences. Here's an example of another question that's like that. So in a room with a staircase leading to the second floor, how can you figure out the height of the first floor ceiling? this is maybe something that's never occurred to you in your life, but you now can learn from that a new method for measuring the height of a ceiling when there's a staircase leading up to the next floor. We can do it right now. I can walk up these stairs here. No, they're not all the same height. I wanted to see, what the extent of these brain play questions is. There's a nice book of the Cognitive Neurosciences that Gazzaniga and Mangan come out with every few years. It's actually an interesting book because it's like first edition, second edition, third edition, fourth edition. And actually each edition is completely different. The questions, the chapters are just whatever chapters they came up with for that edition. So you actually have to get all the editions if you really want to follow that. But it's nice because it has an organization by sections of kind of what is the brain and what's intelligence. And I did an inventory of the brain play questions, and they span a lot of the areas of human intelligence. So that's another reason why I think that it's a good set of questions for as an AI task. I also studied what types of knowledge and what types of reasoning would be required, just kind of going through the questions and making a guesstimate about what I thought would be needed to answer that question. These are the knowledge structures needed. Using my own ontology, scripts. A lot of questions are sort of scripts or stereotypical situations that are common in the everyday world. Plans and goals are pretty important. Then physics, then basic properties and attributes, human body. It's sort of trailing off. Interpersonal relations. There are also episodic memory. There are even questions that ask about the child's experience. And I was thinking, you could throw those out, but then again, we're trying to build AI, so why not leave those in, and maybe the AI can tell about its past experiences. This is now the table that shows what types of reasoning I thought would be required to answer those types of questions. So some of them are database retrieval. These don't add to 100 because I allowed myself to annotate multiple categories for each question. So database retrieval, simulation is very important in a lot of these questions, usually involving sort of physical domain type things. Planning, comparison of things, episodic memory retrieval. There's some visualization. There's also a few questions that ask the child to invent something or come up with a new product or come up with a new solution to something. So what will it take to build a system that could answer these questions, which I think span a large part of human intelligence? One possibility is to try to combine everything, combine all these techniques, combine machine learning, combine symbolic AI, and build a lot of components that all work together to solve these questions. So this table is just showing some mechanisms that we could use, and showing the things I was talking about in the previous part of the talk, whether they're present in that thing, and some don't have them. I think learning is a component that's needed in learning is a thing that's needed in most of the components to be able to scale this up to handle new questions. And I think I've been reading these deep learning papers, and I think even deep learning people agree with this sort of thing. For example, in this deep learning paper that came out in Nature recently, toward the end of the paper they say, ultimately major progress in artificial intelligence will come about through systems that combine representation learning with complex reasoning. And another paper that talks about story understanding, saying that there's still many queries requiring complex inference, in other words, reasoning, multi-step inferencing, that our models are not yet able to answer. As far as these AI challenge problems or tasks, there are a couple of related tasks that have been proposed and are being worked on right now that are interesting. There's the Aristo project at Paul Allen's Institute for Artificial Intelligence, where they're working on getting a system to be able to answer elementary school science questions. There's also this baby task at Facebook, which is answering questions about simple stories. They're actually, you can solve them with the event calculus very easily, but their purpose is to push machine learning systems to be able to handle time, which I think is a good thing. And there's a similar task at Microsoft called the MC test task, which is another story on answering questions about simple stories. In computational linguistics, there's also this recognizing textual entailment task, RTE, which is determine whether one text entails another hypothesis H, or whether it contradicts the hypothesis, or whether you don't know. And that's a very general task that can be used to pretty much do anything in AI. So, you know, they've worked on that, and they have competitions with that, and they've explored different niches of that, and that work is ongoing. And there's also a task VQA that's being done at Virginia Tech and Microsoft, which is answering questions about images. And some of those questions are very common sense-like that would be, you know, require a significant amount of reasoning to be able to answer. There's also at the MIT Center for Brains, Minds, and Machines, there's a Turing++ questions that are similar to that for evaluating the progress that they're making there on the work they'll be doing, sort of also neural modeling and symbolic modeling. To summarize, to build true AI system, facts aren't enough. We need something like predicate logic. We need reasoning about time. We need declarative methods. And these can and should be integrated with machine learning. And I hope you all will do this. So I'm going to leave you with a few thought-provoking questions, like highlights. Can computers reason without symbolic representations? Can computers explain their reasoning to humans without symbolic representation? Is human reasoning fundamentally symbolic? What is the difference between language and symbolic representations? I have my thoughts, but I don't know if I'm right. Anyway, thank you, and for more information, you can see my websites.
So this example that you gave, where you asked the child how can they calculate the height of the ceiling and there is a staircase, can you outline how it could be tackled now in a way that is not far too specific to a particular question?
So I think that it's we have to have definitely modeling physical domain knowledge to do these types of questions. So it's a question, you know, we need to make a decision about how simple we're going to start out our worlds as being. We can't handle probably any question that you're going to be thrown, that's going to be thrown at you in brain play with any, you know, the complex world that it is. So we probably have to start out with a kind of micro world to do things like that. So probably we need physical knowledge about steps and blocks and things like that, where we can do a simulation. How would you figure out to get up to measure the height? That's a hard one. I mean, you can imagine a thing that would try walking up the stairs and maybe incrementing a counter as it walked. You could almost write a program, and that would lead it to, eventually it would realize when it was at the top, hey, I just calculated the height of the ceiling. But I don't know. It's a very interesting problem. But how much do we want to try representing this knowledge in advance, and how much do we want to learn it? Does that help, or do you?
It's an honest answer, because
Yeah.
I was worried that you would say we would have a model of the world where we know that the height of the stair is the number of the steps down, and yeah.
Right. It doesn't use the event calculus. It has some temporal reasoning components that are used to answer questions that involve years. when things happened in history, and can do certain temporal inferences that, if A came before B, then B, and B came before C, then A has to come before C, and things like that. I'm going to go up there for a second. Yeah, go ahead.
I was wondering about the example you gave where the answer where they either walk or run. Do you consider answer where they walk half distance and then they run, or they came back and then they walk? Similar answer to.
Yeah.
So if we add time, let's say, there are infinitely many solutions to this question.
Yeah, that's typically in the event calculus, you have a limited, in these toy problems, you have a limited set of time points, like two time points or 3 time points or something. This, I think, problem is addressed a little. This problem came up also in the satisfiability planning area, where they were trying to figure out an optimal plan, and using satisfiability solving, they would they would do a binary search starting out with 256 time points. They would see, is it soluble? Yes. Then 128, then 64, and if it was not soluble in 64, then they would go up to whatever 64 plus 30, and they would use that to do it. That's because you're quantizing time. I think you can handle this kinds of, it gets back to the frame problem, right? The frame problem is, how do you know what, given any scenario, anything could have happened in between it at any point, and it can completely change everything. So the whole point of the event calculus was to assume that the unexpected doesn't occur unless you're told that it occurs. So we make that assumption, but as you point out, there are many solutions to these problems in general.
Yeah. So I really agree with one of the last points you talked about. The next directions of AI are basically together all this logic-based AI with these other more noises. So how do you envision that happening in the wild guess?
Well, I mean, one thing is neural nets and all the formalism frameworks that people have come up with are just one possible way of doing it. And what about the structure of the way you set up the neurons and stuff can be used to represent time better? If you can figure out how to build a better structure that maybe is closer to what you're trying to get to, then that might work. But that's one idea. It's sort of an area I'd be interested in knowing about. Any ideas in this area and breaking research. It's kind of a wide open thing to look at right now.
So regarding Watson, the two uses you mentioned are both question and answers, but recently they use cooking. I wonder how that implementation differs.
Right. The cooking stuff is under the rubric of Watson, but it does not rely on the original Watson question answering technology. It uses a separate data mine or separate kind of, it's like a data mining by analogy to recipes type framework that was developed originally separately from Watson.
Thing that you mentioned again, right? Suppose that physicians have a mental model of a physical human body when they're doing medical problems. Has IBM thought about trying to link this constraint to these?
There have been I don't know of any projects doing exactly that. There have been a few simulation-related projects at IBM. There was the Blue Gene project to simulate protein folding using supercomputers, and there's a project to simulate the brain with all its, an attempt to simulate at a certain level of granularity all the connections between in an actual artificial brain that I don't think actually based on real data of an actual brain, but to simulate brains. And the WatsonPaths project was an attempt to start to get toward more causal models of medical reasoning, but there hasn't quite been, there may be now, there's a whole new IBM healthcare division that's starting up, possibly. That's one of the things they'll look at.
From looking at the ones that he got wrong, is there anything, those questions that just you need more knowledge and it's just so hard? Anything that strikes you?
I mean, one thing that comes up is kind of a lack of common sense reasoning, whatever that is, but in general it tends to be a long laundry list of things that where each one of them is very hard. Otherwise, we would have just solved that one thing, gotten it up 10% from there.